Okay, here we be. Let's get to another case, a different type, one we haven't seen before. Now, we're going to deal with what we call repeated factors, and we're going to do a couple of them. I'm actually going to solve these. Notice there's not even an integral in here. Just want to show you how it's going to get set up. Well, we have to factor the denominator first. And again, do we see that the degree up top is smaller than the degree down below? Yep. And then we factor out the bottom. That wasn't so bad. We got x squared times x minus 2. Now, if we have a square on any term, or a cube, or to the fourth, that means we're going to have to write it a little bit differently. This is going to be our setup. It's a over x plus b over x squared. We need to have all of the different factors, right? Isn't it x times an x in there? So that means x is one of the factors in the denominator. So we'd have to run through as such, and c over our x minus 2. And then we'd need to perform the same thing. Now, what if the problem was like this? What if it was x to the fourth minus 2x cubed? Well, then we would end up with a problem like this, where you factor out an x cubed and be left with an x minus 2. Therefore, you would have an a over x. Now, this x cubed, we have to deal with the x squared, and the x cubed. We have to count all the way up. And then we'd end up with a d for the x minus 2. So we have to take care of all of those, everything leading up to it. If it was x to the fifth, we'd have to write down an x squared, x cubed, x to the fourth, and x to the fifth. You won't see an x to the fifth. Typically, it's just an x squared, but I want you to see how this works. So if anything is ever raised to a power, we actually have to take care of the first, the second, all the way up to that nth power, whatever that power may be. All right, so let's check it out. Let's see if we can't do this integral now. Let's just check it out. Throw a little dx in there. Well, I don't want to do this. I don't want to do the equal sign. So we're just looking at this one. So we moved over, and we bring it down. And we're going to deal with this PFD. So as per usual, we're going to multiply by, to clear this, is whatever the denominator is. So it's x squared times x minus 2, and we bring it down. Like, okay, we got 5x squared minus 3x plus 2 is equal to. So you bring this in, you're going to be left with a times x minus 2. You bring this one over to that piece, you're going to end up with b times x minus 2. The x squared is just canceled. And then lastly, you're going to end up with c times x squared. Well, we can see that there's a nice clean number we can use to clear it out, but I don't believe you're going to end up getting all of your variables. If we choose x equals 0, yeah, we can solve for b. If we choose x is equal to 2, we can solve for c. But how the heck are we supposed to get a? This is where we have to do the long method. You see that sometimes we can do it, but with these repeated linear factors, that's kind of the term for this, repeated linear factors, we're going to actually have to play that game. So this is 5x squared minus 3x plus 2. Why am I writing that? So we're going to get ax squared minus 2ax. We're going to get bx minus 2b. And we're going to get a cx squared. So now let's put all of our x squared terms together. That's just an a and a c. A plus c x squared. Let's take all of our x terms. That's negative 2a plus b times our x. And then we're left with minus 2b is equal to 5x squared minus 3x plus 2. That means that a plus c must equal 5, equating coefficients. We would find out that negative 3, well, what's that equal to? It's equal to our negative 2a plus b. And lastly, we'll have our negative 2b will be equal to 2. And this one is not so bad. We have a linear equation, but hey, come on. B is equal to negative 1. We got our b value. Once that's done, we can now plug it in and solve for a. Now we have negative 2a plus our b, which was negative 1, is equal to negative 3. So we add over our 1, we get negative 2a. Add 1, we get negative 2. Oh, a is equal to 1. Well, now we can just plug it in right there, and we're like 1 plus c is equal to 5. Come on, man. C is equal to 4. Had to do it the long way. We could have got a couple of them, but we wouldn't have been able to get all of them. So we can say that this is equal to the integral of, so our a was 1, so we get 1 over x, plus negative 1 over x squared. And then our c was 4, so we get 4 over x minus 2 dx. Now let's solve this uber difficult integral. That's the nice piece about PFDs. The algebra at the beginning is kind of rough, but come on, man. The calculus is not so bad. All right, so 1 over x is antiderivative, of course, is natural log of the absolute value of x. This, we're going to add 1 to our exponent, so that's going to become a 1 over x, x to the negative first power, and then we need to divide by that number, which is just going to make it positive. Next, we're going to be left with 4 times, and then we have 1 over x plus 2. That's got to be the natural log of the absolute value of x plus 2, all plus c. So there it is. There's that longer method, how it is forced. So when you have what we call repeated linear factors, anything with a square, a cube, to the fourth means we're going to have to write it out long term. It also means we're going to probably have to go the long way. Oh, there we are. There's another one. So next, we're going to get a little weird. Okay? We're going to deal with a new type of form. Okay.